What if everything we see, touch, and experience, the stars, the planets, life itself, began not with a fiery explosion, but with something far stranger? What if the universe started not with a bang, but a whisper, a moment of profound stillness and connection so subtle, so elegant, that it set the stage for all that would follow? Picture for just a moment a cosmos that hasn't yet learned how to be a cosmos, a swirling, chaotic sea of particles, each one dancing to its own rhythm. No structure, no order, no galaxies, just pure, beautiful quantum noise. And then something shifts, something profound. For the very first time, these particles begin to listen to one another. They begin to cooperate. They fall into sync, not through force, but through harmony. This moment, the universe's first quantum coherence, is where our story truly begins. It's a story that reaches far beyond equations and lab experiments. This is about the origins of reality, how something as vast, as complex, and as breathtaking as our universe could emerge from what seemed like utter randomness. Think about it, the same phenomenon that allows particles to communicate across vast distances, that gives rise to superconductors and quantum computers, might also hold the key to understanding existence itself. That first spark of coherence didn't just create matter, it created meaning. It set in motion the laws of physics, the formation of atoms, the birth of stars, and eventually the rise of conscious beings like us, looking back and wondering how it all came to be. In this video, we're going to explore 30 incredible theories about that pivotal moment. We'll journey from the farthest edges of theoretical physics to the deepest questions about our place in the cosmos. You'll hear ideas that challenge everything you thought you knew about reality, theories that suggest the universe didn't just form but awakened. And by the end, you might just see the world and yourself in a whole new light. So settle in, open your mind, and let's dive into one of the greatest mysteries of all, how our universe found its voice. Our journey begins with a theory that reaches back to the very concept of perfection and its necessary shattering. To understand it, we must first envision a state of existence so uniform, so balanced that it defies our everyday experience. This was a reality of pure potential, a cosmic canvas where every point was identical to every other. There was no here or there, no before or after. The fundamental forces we know today, gravity, electromagnetism, the strong and weak nuclear forces, were fused into one, unified under a single, magnificent law. In this state of perfect symmetry, nothing could happen. For anything to occur, for any story to begin, that perfect, static equilibrium had to break. This shattering of perfection is what physicists call symmetry breaking. And it is within this profound transition that our first theory suggests quantum coherence was born. Think of it like a vast, motionless ocean, every water molecule perfectly aligned with its neighbor. Then, a single, infinitesimal shift occurs. One molecule moves, and that movement is instantly communicated to the trillions of molecules around it. They don't just move randomly, they move together, falling into a coordinated, coherent dance. In the newborn universe, this wasn't water. It was the fabric of spacetime and the quantum fields that live within it. The first coherent behavior wasn't a single particle waking up. It was the entire system shifting as one, transitioning from a silent, featureless state into a universe humming with coordinated potential. This initial coherence provided the scaffolding for everything to come. Before this moment, there was no distinction between matter and antimatter, particles and forces. They were all part of an undifferentiated whole, but as the universe cooled and expanded, that first coherent shift created the conditions for differentiation. It was the universe's first decision, setting the rules that would allow quarks to combine into protons, for atoms to form, and eventually for stars to ignite. This theory posits that the universe didn't just get louder, it got more complex, and it did so through a synchronized quantum event that echoed through all of spacetime. establishing the first rhythm to which all subsequent matter would dance. But how could that initial, delicate coherence spread across a universe that was expanding at a mind-bending rate? This brings us to our second theory, which proposes that the very mechanism thought to have blown up the cosmos was also the conductor for its first symphony. We're talking about the inflationary quantum coherence hypothesis. To grasp this, you have to envision the universe in its first sliver of a second, undergoing a growth spurt so violent it makes every explosion you've ever seen look insignificant. In a time span shorter than a blink, the entire cosmos expanded by a factor of trillions upon trillions. This was the inflationary epoch. Now, imagine quantum fields in that seething, newborn reality. They were buzzing with wild, random fluctuations, a chaotic static of potential. But according to this hypothesis, inflation didn't just stretch space, it stretched and smoothed those quantum jitters, forcing them to synchronize. It's like taking a million out-of-sync metronomes and placing them on a sheet that is being pulled taut at an unimaginable speed. The incredibly rapid, smooth expansion would have forced all their ticks to gradually align, creating a single, coherent rhythm across an enormous region. What was once a cacophony of individual quantum notes became a harmonious chord resonating across the entire cosmos. This synchronized quantum hum, imprinted onto the fabric of spacetime during inflation, became the ultimate cosmic blueprint. Those first coherent quantum fluctuations were no longer microscopic quirks. Inflation had magnified them to astronomical proportions. They became subtle variations in density, slightly denser patches where gravity would eventually get a stronger grip. And it was these very patches, these seeds of structure born from that primordial coherence, that later drew in matter to form the very first galaxies, stars, and ultimately everything we see in the night sky. So the grand tapestry of the cosmos, every cluster, every filament, every vast empty void might just be the fossilized echo of the universe's first moment of quantum cooperation, stretched and frozen into the heavens by the incredible power of inflation. This next theory might be the most radical of all, suggesting that our entire three-dimensional reality, you, me, the stars above, is nothing more than a magnificent projection, a cosmic hologram. The holographic principle proposes that all the information needed to describe our universe is actually encoded on a distant, two-dimensional surface that surrounds us. It's the idea that the world we experience is a kind of illusion, much like a 3D image projected from a flat, two-dimensional screen. And within this mind-bending framework lies a profound possibility that the universe's first act of quantum coherence didn't happen within space but created space, emerging from the synchronized interactions on that primordial two-dimensional boundary. To grasp this, think of a more familiar hologram like the one on your credit card. Tilt it, and you see a three-dimensional image, yet all the information to create that image is contained on the flat, metallic surface. The holographic principle applies this same concept to the entire cosmos. It suggests that in the very first moments, what we perceive as our 3D universe was actually a lower dimensional boundary, a surface buzzing with quantum bits of information. For our reality to project from that surface, those bits couldn't be random. They had to be deeply, intricately linked. They needed to achieve coherence. This theory posits that the first quantum coherence was the moment these information bits on the boundary became entangled and synchronized, their unified state then projecting inward to manifest as the coherent, structured space-time we inhabit. This initial coherence on the cosmic boundary would have been the genesis of everything. It transformed a chaotic, information-rich surface into an ordered, encoded message. That message, when read a certain way, is our physical reality. The gravitational pull of a black hole, the spin of an electron, the very fabric of the vacuum, all of it is a translation of that coherent two-dimensional data. So, in a very real sense, the universe didn't just find its voice. It sang itself into existence from a lower dimensional realm. the first galaxies, the first stars, and the forces that shaped them were all born from that initial, coherent hum of information on the edge of everything, a symphony written in 2 dimensions that we experience in 3. Now we arrive at a theory that takes us to the ultimate limits of reality, to a realm so small, so energetic, that our very conception of space and time begins to break down. This is the domain of quantum gravity, and our 4th theory proposes that the very first quantum coherence was not an event in the universe, but an event of the universe, a moment when the fabric of spacetime itself achieved a state of perfect sync. To understand this, we must journey to the Planck scale. Imagine shrinking down smaller than an atom, smaller than a proton, down to a size of 10 to the negative 35 meters. At this unimaginably tiny scale, the smooth, continuous spacetime described by Einstein's general relativity is no longer smooth at all. Instead, it is believed to be a seething, chaotic froth, a quantum foam. In this foam, tiny wormholes might blink in and out of existence, and the geometry of space itself fluctuates wildly. It's a turbulent ocean of pure potential, where the concepts of here and there lose all meaning. According to the quantum gravity birth theory, it was within this frenetic foam that the first coherence emerged, before particles, before forces, even before a clear distinction between space and time. The geometry of reality itself began to find a rhythm. Think of it like the surface of a boiling pot of water. At first, bubbles form and pop at random, a chaotic mess of activity. But if you could watch for long enough, you might start to see patterns emerge, regions where the bubbles seem to form in sync, creating a temporary, organized structure. The theory suggests that a similar thing happened in the quantum foam. Through a process governed by the elusive laws of quantum gravity, microscopic regions of spacetime, perhaps trillions of them, suddenly fell into a coherent state. Their wild fluctuations synchronized, and for the first time, a stable, albeit tiny, geometry was born. This wasn't just coherence among particles. This was spacetime achieving coherence with itself, creating the first stable islands of order in a sea of chaos. This initial coherence of spacetime geometry would have been the foundational event for everything that followed. A stable fabric of space and time is the ultimate prerequisite for matter and energy to even exist in any recognizable form. Particles need a consistent stage upon which to perform. This theory posits that the first quantum fields, which would later give rise to electrons and quarks, were able to emerge and themselves achieve coherence because the stage beneath them had already become stable and synchronized. The coherent humming of spacetime geometry provided the harmonic foundation that allowed the first particles to join the symphony, setting in motion the chain of events that led from a frothy void to a structured, law-abiding cosmos. This leads us to a theory so profound and controversial that it challenges the very nature of reality and our place within it. It's the idea that consciousness, the phenomenon of subjective experience, isn't just a late-arriving product of the universe, but was somehow present at its birth, playing an active role in shaping the cosmos from the very first moment. This is the consciousness-created coherence proposal, and it ventures into territory where physics, philosophy, and metaphysics beautifully and bewilderingly collide. The foundation of this idea rests on one of the strangest and most well-tested observations in all of quantum mechanics, the measurement problem. In the quantum world, particles exist in a haze of probability, a superposition of many possible states. An electron isn't definitively here or there. It's in a blend of locations, spins, and energies. But the moment we observe it, the moment we measure it, that fuzzy cloud of possibilities seems to collapse into a single, definite reality. The act of observation itself appears to force the quantum system to make a choice. For decades, physicists have debated what exactly constitutes an observation. Is it the interaction with a measuring device, or does it require a conscious mind to finally pin down reality? Some theorists, like the renowned mathematician John von Neumann and later Nobel laureate Eugene Wigner, took this idea to its logical extreme. They proposed that consciousness itself is the fundamental agent that causes the wave function to collapse. Without a conscious observer, reality remains in a state of unmanifest potential. Now extend that thought back in time, all the way back to the beginning. If consciousness is required to collapse quantum possibilities into definite realities now, could it have been necessary then? This theory posits that the universe's first great act of quantum coherence, the shift from possibility to actuality, was itself a form of primordial observation, a cosmic act of measurement that gave birth to reality. But who or what was doing the observing? This is where the theory splits into breathtakingly different paths. One perspective suggests a kind of cosmic consciousness, a universal mind that existed before the physical universe as we know it. In this view, the first coherence was the universe becoming aware of itself, a self-observation that crystallized the laws of physics and initiated the flow of time. Another, even more radical interpretation doesn't require a separate observer at all. It suggests that the universe and consciousness are two sides of the same coin, emerging together in a single, coherent event. The first particles didn't achieve coherence and then later give rise to conscious beings. The achievement of coherence and the dawn of proto-consciousness were one and the same process. This proposal forces us to reconsider our entire cosmic story. It implies that the seeds of mind were woven into the fabric of the universe from its very first instant. The evolution of galaxies, stars, and planets wasn't just a random march toward complexity that eventually, accidentally, stumbled upon consciousness. Instead, it was a universe gradually unfolding a potential that was always there, moving toward greater and greater expressions of that initial conscious coherence. In this light, our own human consciousness isn't a tiny, insignificant flicker in a vast, mindless void. It is the universe itself become aware, remembering and reflecting upon its own astonishing origin. Yet this line of thinking leads us to an even more staggering possibility. If an infinite number of universes are constantly bubbling into existence, each with its own random set of physical laws, then the fact that we find ourselves in one with stable coherence and life might not be a miracle at all. It might simply be a consequence of our own existence. This is the anthropic principle in its strongest form. We could only ever observe a universe capable of producing us. We are not witnessing a selected universe, we are the selectors simply by virtue of being here to observe it. Our conscious observation is what, in a sense, makes this particular cosmic symphony real to us, while the silent, chaotic universes remain forever unobserved and unrealized. This theory doesn't so much solve the mystery of our universe's perfect coherence as it reframes it, placing our own existence at the very heart of the cosmic narrative. But to truly grasp the scale of this idea, we have to consider the nature of dark energy itself. We often picture it as a kind of anti-gravity, a mysterious pressure inflating the universe like a balloon. But what if that description misses the mark entirely? What if dark energy isn't a force acting upon space, but is instead a property of space itself, a fundamental energy woven into the vacuum of nothingness? This is the concept of the cosmological constant, an idea so intriguing that even Einstein proposed it, though he later called it his greatest blunder. This theory suggests that the energy of empty space isn't zero. It has a small, positive value that causes the universe to expand at an accelerating rate. The question then becomes, where did this vacuum energy come from? The dark energy coherence connection posits an answer. It is the faint, leftover hum of the universe's first and greatest act of quantum synchronization. Think of it like a vast, quiet hall after a grand symphony has ended. The musicians have packed up and left, the audience has gone home, but if you stand perfectly still and listen closely, you can still hear a faint echo reverberating off the walls, a lingering memory of the music that once filled the space. In this analogy, the explosive birth and the frantic particle creation of the early universe were the symphony. the initial pervasive quantum coherence was the music itself. And dark energy, the subtle force accelerating galaxies away from each other, is that enduring echo. It is the residual energy of that first coherent state, a whisper of synchronization that was imprinted onto the very fabric of spacetime and has been stretching it apart ever since. This perspective offers a breathtakingly elegant solution to one of the biggest puzzles in modern cosmology, the cosmological constant problem. Physicists have calculated that if the vacuum energy comes from the random jitters of quantum fields, its value should be enormous, perhaps 120 orders of magnitude larger than what we observe. This discrepancy is often called the worst prediction in all of physics. But if the vacuum energy isn't just random noise, but is instead the fossilized energy of a coherent state, its value could be naturally small and uniform. Coherence implies order and coordination, which would suppress the wild, random fluctuations and leave behind only a smooth, subtle energy, exactly what we measure dark energy to be. In this view, the incredible weakness of dark energy isn't a problem. It's powerful evidence that the universe began not in chaos, but in a state of profound harmony. This brings us to a theory that hinges on one of the most baffling and confirmed phenomena in all of physics, a connection so intimate and instantaneous that it seems to defy the very nature of space and time. Albert Einstein famously dismissed it as spooky action at a distance, but quantum entanglement is very real. It's the bizarre process where two particles become linked so profoundly that measuring the state of one instantly determines the state of the other, no matter how many light years apart they are. It's as if they share a single existence. The quantum entanglement origin theory proposes a breathtakingly simple yet profound idea, that the universe's first coherence wasn't a sudden event that happened to particles, but was instead their natural, original state. In the beginning, everything was entangled with everything else. To visualize this, imagine the newborn universe not as a collection of separate, independent entities, but as a single, vast, interconnected quantum network. Every point was in immediate communication with every other point. There was no such thing as true separation or isolation. This cosmic web of entanglement meant the entire system behaved as one unified whole. Its properties were not defined by individual parts but by their inseparable connections. In this view, coherence wasn't an achievement, it was the default setting of reality. The universe didn't need to find harmony because it was born perfectly in sync, a grand cosmic chord where every particle was a note intrinsically tied to all the others. But if that's true, why does our universe today appear so disconnected? Why don't we see these spooky links in our everyday world? This is where the second part of the theory comes in, and it involves a process known as decoherence. The perfectly entangled, coherent state of the infant universe was incredibly fragile. As the cosmos expanded and cooled, this pristine quantum network began to fray. Particles started interacting with their environment, colliding with others, being influenced by emerging quantum fields. Each of these interactions acted like a tiny pair of scissors, snipping the delicate threads of entanglement that bound the universe together. This gradual decoherence wasn't a flaw, it was essential for the creation of the classical world we know. For the universe to evolve from a unified quantum whole into a realm of distinct galaxies, stars, and people, it had to lose some of its perfect coherence. The blurry, probabilistic quantum world had to give way to the definite, concrete reality we experience. This theory suggests that the world we see around us with separate objects and clear boundaries is the result of most of those primordial quantum connections having been severed over billions of years. The spooky action is still there, but it's buried deep under trillions upon trillions of subsequent interactions, like a faint whisper drowned out by a roaring crowd. Yet, the ghost of that original state may still be visible to us today. The large-scale structure of the universe, the great cosmic web of galaxies and filaments, shows correlations that are difficult to explain through local interactions alone. Galaxies billions of light-years apart seem to be aligned in ways that suggest they were once in contact. This could be the fossilized imprint of that initial universal entanglement, a memory of when all points in space were neighbors in the quantum network. So, while we now perceive a universe of separate things, its underlying foundation might still be one of deep, invisible connection, a silent testament to its perfectly coherent and utterly entangled birth. This brings us to a theory that tackles one of the most fundamental and puzzling features of our existence, the relentless one-way flow of time. Why do we remember the past but not the future? Why does an egg scramble easily but never unscramble itself? This directionality is known as the arrow of time, and its most famous driver is the second law of thermodynamics, which states that the total disorder or entropy of a closed system always increases. The universe, it seems, is on a one-way trip from order to chaos. But what if this entire journey, the very reason time has a direction at all, was set in motion by that first pivotal moment of quantum coherence? The thermodynamic arrow theory proposes exactly that, suggesting coherence didn't just happen in time, but was the event that gave time its arrow. To understand this, we have to rethink the very beginning. The classic Big Bang model often presents a universe starting in a state of incredibly low entropy, a condition of exquisite order and homogeneity, a perfectly smooth, ultra-dense soup of particles. This has always been a profound puzzle for physicists. Why would the universe start in such a special, ordered state? The thermodynamic arrow theory offers a radical inversion of this perspective. It suggests that perhaps the very early universe wasn't a state of low entropy at all, but was actually a state of maximum entropy, a state of total equilibrium and ultimate disorder. In this view, the initial cosmos wasn't a smooth soup. It was a featureless, randomized haze where nothing could happen because everything was in perfect, boring balance. Time had no direction because there was no way to distinguish past from future. The catalyst for change, according to this theory, was the emergence of quantum coherence. This was the event that broke the symmetry of this maximum entropy state. Think of it like a vast, motionless, and perfectly flat sea. There is no current, no flow, no way to tell one direction from another. Then a single, coordinated wave begins to form. That wave is coherence. It introduces a direction, the direction the wave is moving. In the same way, the universe's first great act of synchronization created a fundamental asymmetry. It provided a reference point, a before and after. Before coherence, there was only random noise. After coherence, there were correlated patterns, organized structures, and a clear path from a less ordered past to a more ordered, albeit transient, future. This initial push away from maximum entropy is what set the thermodynamic arrow in motion. The second law of thermodynamics isn't a fundamental law that causes the increase of disorder. It is a description of the universe's inevitable slide back toward the equilibrium from which it first escaped. Coherence created pockets of beautiful, temporary order, the first particles, the first forces, and in doing so, it created a debt of disorder that the rest of the universe has been paying back ever since. The scramble of an egg, the cooling of a star, the expansion of the cosmos, these are all part of the universe's long, slow return to its original state of featureless equilibrium. The first quantum coherence was the singular event that wound up the cosmic clock, and everything that has happened since is the sound of that clock ticking down. Now we venture into a realm where the very building blocks of reality are not dots but tiny, vibrating loops of energy. This is string theory, and our 10th theory proposes that the universe's first quantum coherence was not a synchronization of particles, but a symphony of strings. A moment when every fundamental vibration in the cosmos suddenly found the same perfect pitch. To grasp this, we must shrink our imagination smaller than we ever have before. Forget about point-like electrons and quarks for a moment. Picture instead that every fundamental particle is actually an unimaginably small, one-dimensional loop or a tiny open strand, vibrating in a universe with many more dimensions than the three of space and one of time we experience. These are strings, and just like the strings on a violin or a guitar, how they vibrate determines everything about them. A string vibrating one way might be an electron. The exact same type of string vibrating a different way might be a photon, the particle of light. The mass, the charge, the very identity of every particle is dictated by the note its string is playing. In the furious energy of the early universe, these strings would have been vibrating chaotically, each one producing a cacophony of different clashing notes. There was no consistency, no stability. An electron string might flicker into a photon string and back again. The very concepts of matter and force were not yet distinct. The string theory vibrational coherence hypothesis suggests that a profound shift occurred when the expanding universe cooled to a precise, critical energy. At that moment, the vibrations of these strings didn't just change, they locked into harmony. Trillions upon trillions of identical strings all across the nascent cosmos began to resonate at the same fundamental frequencies. This was the first great musical chord of the universe. This synchronization of vibrations would have been the moment the first stable particles truly emerged. Before this coherence, there were no persistent electrons or quarks. After it, there were. The harmonious vibrations created a stable, lowest energy state, a ground note for each type of particle. This coherence didn't just create matter, it also dictated the forces. The theory proposes that the force of gravity, for instance, is mediated by a specific string vibration called the graviton. The coherence that locked in the electron's vibration would have also locked in the graviton's vibration, simultaneously establishing both the actors and the rules of the cosmic play. The four fundamental forces we know today may have unified into one superforce, not because they were the same thing, but because the strings that carried them were all vibrating in a perfectly coordinated, coherent symphony before the great cooling forced them to specialize into the distinct notes we observe now. This perspective offers a breathtakingly elegant vision of cosmic origins. The universe didn't start with a bang, but with a ring, a single pure tone that organized all of reality. The search for a unified theory of everything is, in this light, the search for the ultimate musical score from which all of existence is played. The laws of physics are not arbitrary rules. They are the necessary harmonics that allow these strings to vibrate in a stable, coherent cosmos. And in a beautiful twist, this theory suggests that the music never stopped. Every particle in your body, every photon of light reaching your eyes, is a tiny string still vibrating, still playing its part in the endless symphony that began at the dawn of time. This brings us to a theory that applies one of biology's most powerful ideas to the birth of the cosmos itself. We are all familiar with Darwin's theory of natural selection, the process by which random variations in living things are tested against an environment, with the most successful traits surviving to be passed on to the next generation. But what if a similar process of selection wasn't confined to the realm of biology? What if it operated on the most fundamental level of reality at the very beginning, acting not on genes but on quantum states? This is the core of quantum Darwinism, a proposal that the universe's profound coherence wasn't a guaranteed outcome, but the winning ticket in a cosmic lottery where only the most stable and resilient quantum states survived. To understand how this might work, we need to picture the infant universe not as a single, defined reality, but as a seething cauldron of possibilities. Every conceivable quantum state flickered in and out of existence, each one a potential version of reality. Some of these states were wildly unstable, collapsing almost instantly back into the quantum noise from which they emerged. Others were slightly more persistent, lasting a fraction of a second longer. In this chaotic environment, a form of natural selection took hold. The unstable states were like genetic mutations that are immediately fatal. They simply couldn't persist. The states that survived even a moment longer had a crucial advantage. They could interact with their environment and, most importantly, be copied. This is where the Darwinism truly comes into play. A quantum state achieves stability not just by existing, but by imprinting copies of itself onto its surroundings. Imagine a single, coherent quantum system. For its particular state to become a permanent feature of reality, it must leave a mark. It must be measured and recorded by other parts of the universe. The most successful states are not necessarily the most powerful or energetic. They are the ones that are the most shareable, the most effective at getting their information copied and disseminated. They are the ones that countless other systems can independently measure and agree upon, creating a consensus reality. In this fierce competition for existence, the quantum states that were robust and reproducible outlasted their fragile competitors. They were selectively amplified, their coherent patterns spreading and becoming the bedrock upon which our classical world was built. This theory provides an elegant explanation for why our universe appears so classical and definite to us, despite being built on a fuzzy, probabilistic quantum foundation. We don't see all the strange superpositions and entangled states because they were the losers in this early evolutionary struggle. They were too delicate to withstand the constant interactions and decoherence of the expanding universe. The states we do observe, the position of a planet, the momentum of an asteroid, the charge of an electron, are the grand champions of quantum Darwinism. They are the highly stable, redundant states that have been copied so many times across the environment that they have become an objective fact, agreed upon by every possible observer. The universe we see is not the only one that could have been. It is simply the one that was most fit to survive. This brings us to a mystery so deep that it threatens to unravel our understanding of reality itself. A puzzle that pits the two most successful theories in physics, quantum mechanics and general relativity, against each other in a fundamental way. It's called the black hole information paradox, and its potential resolution might just hold the key to understanding how the universe maintained its coherence from the very first moment. To see how these two ideas connect, we first have to understand what the paradox actually is. According to Einstein's general relativity, a black hole is a region of space where gravity is so intense that nothing, not even light, can escape its pull. The boundary of this point of no return is called the event horizon. Now, if you were to throw an object into a black hole, say, a book containing vast amounts of information, classical physics tells us that book is gone forever, irretrievably lost behind the horizon. The problem arises when we bring quantum mechanics into the picture. One of the most sacred principles of quantum theory is that information cannot be destroyed. It can be scrambled, it can be transformed, but it can never be truly erased. The information that described that book must still exist somewhere in the universe. So, what happens to it when the black hole eventually evaporates over eons through a process called Hawking radiation? Does the information vanish, violating quantum mechanics, or is it somehow preserved? This is the heart of the paradox. For decades, physicists have been searching for a mechanism that would allow information to escape a black hole without breaking the known laws of physics. One of the most promising solutions involves a concept called quantum hair, and it's here that we find a stunning link back to the dawn of time. The idea is that black holes are not the perfectly smooth, featureless objects described by classical theory. Instead, they possess subtle quantum mechanical properties, a kind of hair that encodes information about what fell into them. This information isn't stored inside the black hole, but is instead imprinted onto its event horizon and radiated away in a scrambled but preserved form through Hawking radiation. Now, let's stretch this idea back to the universe's infancy. For information to be preserved in this way, for a black hole to have quantum hair, the event horizon itself must be capable of a specific kind of quantum behavior. It must be able to maintain a coherent relationship with the particles that are radiating away. This is a profound act of quantum synchronization across a barrier, a delicate dance that prevents information from being lost. Some theorists propose that this ability isn't a special feature unique to black holes. It might be a relic, a leftover trait from the universe's first coherent state. In other words, the same quantum coherence that allowed the entire cosmos to act as one synchronized system may have also established the fundamental rule that information must always be preserved, creating the protocols that even black holes must obey. This suggests a truly incredible possibility that the universe's initial quantum coherence built information preservation right into the fabric of spacetime. The cosmic network of entanglement that connected all points at the beginning may have set a precedent, creating a universal law that no process, not even the most extreme gravitational collapse, can ever truly break a quantum connection and destroy information. The coherence that birthed the galaxies might also be the very thing that ensures not a single bit of information about them is ever lost, forever woven into the holographic fabric of the universe. Think about water turning to ice. A lake on a cold winter night is a chaotic dance of liquid water molecules, each moving freely and independently. But as the temperature drops below a critical point, 0 degrees Celsius, something remarkable happens. The molecules don't just slow down, they spontaneously organize. They align into a rigid, crystalline structure, moving in a synchronized, coherent lattice. This is a phase transition, a sudden, dramatic shift in the properties of a system driven by a change in its environment. Now, apply this same principle to the source of reality itself. The quantum field phase transition theory proposes that the universe's first great act of coherence occurred in exactly this way, not as a slow gathering, but as a sudden, spectacular cosmic freeze. To grasp this, we need to envision the earliest universe not as a place of particles, but as a sea of primordial quantum fields. These are not physical things in space, but more like the fundamental rules of the game, the invisible entities that permeate all of reality and whose excitations are what we perceive as particles. In the incredible heat and density of the first moments, these fields were agitated and chaotic. The Higgs field, the electron field, the quark fields, they were all in what physicists call a symmetric high-energy state. Their values were fluctuating wildly, like that lake of water on a warm day. There was no mass, no distinct identity for particles. Everything was a blended high-energy soup. But as the universe expanded, it cooled, and just like the lake dropping below 0, it eventually crossed critical temperature thresholds for these quantum fields. This is when the phase transition occurred. The fields, in a sense, had to choose a stable, low-energy state. The theory suggests that this transition didn't happen randomly at different points. Instead, a process called symmetry breaking swept across the entire cosmos. Imagine a chill starting at one end of the lake and spreading instantly, freezing the entire surface into a single, continuous sheet of ice. In the same way, a coherent wave of organization propagated through the universe, forcing the quantum fields to settle into their new, stable configurations in a synchronized manner. This is directly analogous to how superconductivity emerges in certain materials. In a normal metal, electrons bump and scatter, creating electrical resistance. But when cooled below a critical temperature, they undergo a phase transition. Suddenly, electrons pair up and move in a coordinated, coherent flow, a single quantum state that can conduct electricity with 0 resistance. The material doesn't just get colder, its fundamental properties change as it achieves a new, highly ordered state. The theory posits that the entire universe underwent a similar transformation. The first large-scale quantum coherence was the moment the cosmos itself became a superconductor, with its quantum fields locking into a synchronized, zero-resistance state that allowed for the seamless and coordinated birth of the first stable matter. This cosmic phase transition would have been the ultimate organizer. It's what gave mass to particles, carving out the distinct identities of electrons and quarks from the previously uniform energy field. More importantly, this synchronized settling of the fields created the conditions for lasting coherence. It established a uniform vacuum, a consistent background against which particles could interact predictably. Without this universal freeze, the quantum fluctuations from the inflationary epoch might have remained just noisy jitters. But because the fields had now coherently settled everywhere, those tiny density variations were amplified and locked in, becoming the gravitational seeds for galaxies. The universe didn't just cool down, it crystallized into a coherent structure, setting the stage for everything that was to come. And yet, for all these grand theories, a profound and deeply philosophical question remains. Why did the universe develop this specific, delicate form of quantum coherence that led to galaxies, stars, planets, and ultimately to us? It's a question that leads us to our 14th theory, one that shifts the focus from cosmic mechanisms to the very nature of observation and existence. This is the anthropic principal coherence argument, and it proposes a startling possibility. The universe's foundational coherence isn't just a random fact we observe, but a necessary precondition for our very ability to be here observing it. The anthropic principle, in its simplest form, is the idea that any valid theory about the universe must account for the fact that we are here to observe it. We do not find ourselves in a universe that is too hot for atoms, or too empty for planets, or too chaotic for life. We find ourselves in a universe that is, almost suspiciously, just right. This fine-tuning is one of the most enduring mysteries in all of science. The fundamental constants of nature, the strength of gravity, the mass of an electron, the cosmological constant, seem perfectly calibrated to allow for a complex, life-bearing cosmos. Alter any one of them by even a tiny fraction, and the universe would be a barren, lifeless void. The anthropic coherence argument applies this same logic directly to the phenomenon of quantum coherence. For conscious life to eventually evolve, the universe couldn't just be coherent. It had to be coherent in a very specific, highly refined way. Imagine the first moment of synchronization as a dial with a near-infinite number of settings. If the dial had been turned to almost any other position, the outcome would have been a cosmic dead end. Perhaps the coherence would have been too weak, causing the initial density fluctuations to dissipate before they could ever collapse into the first galaxies. Matter would have remained a thin, useless haze, or perhaps the coherence would have been too strong, locking all particles into such a rigid, crystalline state that no movement, no chemistry, and no complexity could ever arise. The universe would have been frozen in perfect, sterile order. Our existence, therefore, acts as a kind of cosmic filter. We could only ever find ourselves in a universe where that first quantum coherence struck the perfect balance between chaos and order, a balance that allowed for the formation of structured galaxies while also permitting the flexible, dynamic interactions necessary for planetary formation and the intricate dance of organic chemistry. The very fact that we are here pondering the origins of quantum coherence is not a coincidence. It is evidence that the coherence we're studying was precisely of the type that could lead to conscious observers. In this view, the universe didn't just happen to develop coherence. In a very real sense, it developed coherence for us because any universe that didn't would remain unobserved and unremarked upon, a silent and empty symphony with no one to hear it. This reasoning splits into two powerful interpretations. The first is the weak anthropic principle, which is more of a selection effect. It simply states that we observe the universe to have certain properties because those properties are necessary for our existence. We shouldn't be surprised to find ourselves in a universe with finely tuned coherence because we couldn't exist in one without it. This is a logical, almost tautological statement. But it leads to a much stronger and more controversial interpretation that the laws of physics and the specific nature of that first coherence are not accidental. This strong anthropic principle suggests that the universe is in some way compelled to develop laws that lead to conscious life. This doesn't necessarily imply a guiding intelligence, but it does point toward a universe with a surprising predisposition for life and mind. When we combine this with the many worlds interpretation of quantum mechanics, the implications become truly staggering. If an infinite number of parallel universes are constantly bubbling into existence, each with its own random set of physical laws and coherence parameters, then it is no surprise that we find ourselves in one of the vanishingly few where everything is perfectly aligned for life. Our universe isn't special, it's just the one we happen to inhabit. The anthropic principle becomes the ultimate answer to the fine-tuning problem. We are not witnessing a selected universe, we are the selectors simply by virtue of being here to observe it. Our conscious observation is what, in a sense, makes this particular cosmic symphony real to us, while the silent, chaotic universes remain forever unobserved and unrealized. This theory doesn't so much solve the mystery of our universe's perfect coherence as it reframes it, placing our own existence at the very heart of the cosmic narrative. This journey through cosmic origins brings us to a fascinating and deeply modern idea, one that draws a powerful parallel between the most advanced technology we are building today and the very first moments of existence. In laboratories around the world, scientists are painstakingly working to create and maintain a special state inside machines called quantum computers. These aren't ordinary computers, they leverage the bizarre rules of the quantum world to perform calculations that would be impossible for any classical machine. And the single biggest challenge they face is a phenomenon called decoherence, the tendency of their delicate quantum bits, or qubits, to lose their synchronized state and collapse into ordinary classical bits. To make a quantum computer work, you have to protect its qubits from the outside world, shielding them from any vibration or temperature change that could disrupt their fragile coherence. It is an immense technical hurdle. Now hold that thought and cast your mind back 13.8 billion years. What if the entire universe underwent a similar process? This 15th theory, the quantum computing cosmic analogy, proposes that our cosmos is in fact the ultimate quantum computer, and that its first moment of coherence was the moment it successfully booted up. Think about what a quantum computer does. It doesn't calculate with definite ones and zeros. Instead, it uses qubits that can be in a superposition of both states simultaneously. This allows it to explore a near infinite number of possibilities all at once, only settling on a final answer when the computation is complete and we measure the result. It's a machine that thrives on potential. Now apply that concept to the origin of everything. The very early universe was a realm of pure potential, a superposition of every possible configuration of particles, forces, and even physical laws. It was computing every possible version of itself simultaneously. The theory suggests that the Big Bang wasn't an explosion in space, but the start of a cosmic computation, a wave function of the universe beginning to evolve. For this computation to produce a stable, structured reality, the one we observe, it couldn't remain in a fuzzy state of all possibilities. It needed to achieve a specific, coherent output. This is where the analogy becomes so compelling. In our man-made quantum computers, we fight decoherence with extreme cooling, vacuum chambers, and magnetic shielding. What provided the shielding for the infant universe? The answer might be inflation itself. That period of faster-than-light expansion could have acted as the ultimate isolation chamber, stretching space so rapidly that the universe's own quantum states were protected from collapsing. It was the perfect environment for the cosmos to process its initial conditions in a coherent superposition, only deciding on a specific set of physical laws and constants once that inflationary period ended and the universe effectively opened the box to look at the result. In this view, the first large-scale quantum coherence was not a random event but the successful outcome of the universe's first and most important computation. The synchronized quantum fields, the locked-in vibrations, the correlated particles, these were the signs of a system that had resolved its initial uncertainty. The cosmos computed its own existence, and the answer it got was the universe we call home. This doesn't just offer a new metaphor for creation. It provides a potential framework for understanding why our physical constants are so finely tuned. Those constants aren't arbitrary. They could be the hard-coded output of that first cosmic program, the logical and necessary answer to the initial conditions of the computation. The implications of this idea ripple forward through time. If the universe is a quantum computer, then everything within it, every galaxy that forms, every star that ignites, every life form that evolves, is part of an ongoing computation of staggering complexity. We are not just inhabitants of the universe, we are patterns within its processing. Our own consciousness, which seems to play a role in collapsing quantum possibilities in the lab, might be an extension of this cosmic process, a localized manifestation of the universe observing and thereby defining itself. The great quest of physics to find a theory of everything could then be seen as the effort to reverse engineer the source code of reality, to discover the fundamental algorithm that the universe first ran at the moment of its coherence, an algorithm that is still running today. This brings us to a theory that challenges our most basic intuition about the nature of reality itself. We experience the world as a smooth, continuous stage, a seamless fabric of space through which we move and time through which we flow. But what if this is merely an illusion, a grand magic trick played on our senses? What if, at its most fundamental level, spacetime is not continuous at all, but is instead granular, composed of tiny, discrete units? The spacetime network coherence model proposes exactly this, suggesting that our smooth reality emerged from a cosmic web of individual quantum connections, and that the universe's first great coherence was the moment this network synchronized, creating the continuous stage we now take for granted. To grasp this, we need to shrink our imagination down to the Planck scale, a realm so small that the very concepts of distance and duration break down. Here, physicists theorize spacetime might not be smooth. Instead, it could be a vast, evolving network of individual nodes or loops, each representing a tiny, discrete volume of space. Think of it like a digital photograph on a screen. When you look up close, you see it's actually made of countless individual pixels, but from a distance, those pixels blend together to create a seamless, continuous image. In this model, the universe is that image, and the pixels are these fundamental Planck scale units of spacetime. In its earliest moments, this network was a chaotic, jumbled mess. The connections between nodes were random and fluctuating. There was no consistent notion of here versus there, no clear direction for time to flow. It was a foamy, probabilistic soup of potential geometries. The pivotal moment, according to this theory, was when this frenetic network achieved coherence. This wasn't about particles syncing up. This was about the very architecture of reality organizing itself. Through a process still not fully understood, the nodes in this network began to form stable, consistent connections with their neighbors. A single, coordinated pattern of linkages emerged and spread. It's like watching a grid of lights flicker randomly, and then suddenly, all at once, they snap into a perfect, interconnected pattern where every light is in communication with every other. This was the moment the quantum foam crystallized. The wildly fluctuating connections between nodes stabilized, and for the first time, a consistent geometry was born. The individual pixels of spacetime synchronized their behavior, and in doing so, they created the illusion of a smooth, continuous fabric. This initial coherence of the spacetime network is what established the fundamental rules of our reality. The speed of light, the gravitational constant, the very dimensionality of our universe, these are not arbitrary numbers handed down from on high. They are the emergent properties of how this underlying network is wired. The specific way in which the nodes achieved coherence determined the number of macroscopic dimensions we experience, locking in 3 of space and 1 of time, while possibly compactifying or closing off others. The strength of gravity, which feels so weak compared to other forces, might simply be a reflection of how sparsely connected the nodes in the gravitational network are compared to those governing other forces. In this view, the laws of physics are not written into the universe. They are the user manual for a system that booted up at the moment of coherence. This model offers a stunningly elegant solution to one of the biggest problems in all of physics, uniting Einstein's theory of general relativity, which describes the smooth, curved geometry of spacetime, with quantum mechanics, which describes the discrete, probabilistic nature of particles. The conflict between the two frameworks has always been that quantum theory suggests a granular reality, while relativity requires a smooth, continuous one. The spacetime network coherence model bridges this divide by suggesting they are both correct, but are describing different levels of reality. Quantum mechanics describes the behavior of the individual nodes, the pixels. General relativity describes the behavior of the coherent network, the smooth image that emerges from those pixels. The theory posits that we don't perceive the granularity because the coherence is so perfect and so complete that the underlying discreteness is hidden from view, just as you don't see the individual pixels on a high-resolution screen during a movie. The universe's first act of synchronization was so effective that it perfectly masked its own quantum origins, presenting us with the continuous, predictable stage upon which the entire cosmic drama would play out. But to truly solve the measurement problem, we need a mechanism, not just a metaphor. This is where the idea of environmental decoherence becomes so powerful. In the modern world, when we try to measure a quantum particle, it's nearly impossible to isolate it. It constantly interacts with its environment, bumping into air molecules, being jostled by the faint glow of starlight, even being influenced by the cosmic microwave background radiation. Each of these tiny interactions acts like a miniature measurement, forcing the particle's wave function to collapse into a more definite state. The environment is continuously and irreversibly recording information about the particle, a process known as quantum Darwinism, where only the most stable, reproducible states survive this constant scrutiny. The reason we see a definite world is not because of a conscious observer in the lab, but because the entire universe is, and always has been, observing itself. Now cast this process back to the very beginning. The infant universe was an incredibly dense, incredibly hot environment. Every nascent particle was in intimate contact with trillions of others. There was no isolation, no vacuum chamber to protect a fragile quantum state. This theory suggests that the universe's first large-scale quantum coherence and the solution to the measurement problem are one and the same event. The initial synchronization of quantum fields wasn't a gentle process. It was a violent, rapid decoherence caused by the ultimate environment, the entire cosmos pressing in on itself. In that first moment, every potential state was measured and recorded by everything else simultaneously. The universe didn't have a choice to remain in a superposition. It was forced into a consensus reality by its own overwhelming density and interconnectivity. This provides a stunningly elegant resolution. The measurement problem exists in our labs today because we struggle to create perfect isolation. But at the origin, perfect isolation was impossible. The first coherence was the moment the universe measured itself into existence. It chose a set of physical constants, a specific geometry, and a direction for time, not through a conscious act, but through an irreversible environmental interaction that locked in those properties. The wave function of the entire cosmos collapsed, not because someone was looking, but because in that ultra-dense state, everything was looking at everything else all at once. The quantum measurement problem isn't a paradox, it's a relic of a time when the universe was so connected that definite reality was the only possible outcome. We live in the aftermath of that great collapse, in a world that was defined in a single, coherent instant, forever moving forward from that first and most decisive measurement. Now we look up into the night sky and see a vast darkness punctuated by stars and galaxies. But if we could see the universe in microwave light, we would witness something truly extraordinary, a perfect, near-uniform glow that blankets the entire cosmos. This is the cosmic microwave background radiation, the oldest light in the universe, a fossilized relic from a time when the cosmos was just 380,000 years old. It is the afterglow of the Big Bang, and etched into its subtle patterns might be the ultimate evidence for our universe's first quantum coherence, a cosmic fingerprint frozen in time. To understand how this ancient light holds such profound secrets, we need to journey back to that pivotal moment, 380,000 years after the beginning. Before this, the universe was an opaque, searing hot plasma, so dense that light particles, photons, were constantly trapped, bouncing off a chaotic soup of free electrons and protons. It was a cosmic fog, and you couldn't see through it. But as the universe expanded and cooled, it finally reached a critical temperature where electrons could be captured by protons to form the first stable hydrogen atoms. This event, known as recombination, suddenly cleared the fog. For the first time, photons could travel freely across the universe. The light that was released at that very instant has been traveling ever since, stretched and cooled by the expansion of the universe into the faint microwave whisper we detect today. This background radiation is astonishingly uniform, but it is not perfectly smooth. When we map it with incredible precision using satellites like the Planck Observatory, we find tiny variations in temperature, minute patches that are ever so slightly warmer or colder than the average. These fluctuations are incredibly small, on the order of 1 part in 100,000, but they are there. And these tiny ripples are not random noise, they are the seeds of all future structure. They are the gravitational blueprints that would, over billions of years, pull matter together to form galaxies, stars, and planets. The crucial question is, where did these precise, specific patterns come from? The leading theory is that they are the magnified and frozen imprint of quantum fluctuations that were generated during the universe's inflationary phase, and crucially, those quantum fluctuations had to be coherent. This is where the connection to our first quantum coherence becomes clear. The theory of inflation posits that the universe underwent a period of exponential expansion, stretching a tiny, subatomic patch of space into our entire observable cosmos. During this inflation, the quantum fields that permeate all of reality were subject to the uncertainty principle, meaning they were buzzing with tiny, random fluctuations. But because inflation stretched space so rapidly and smoothly, it didn't just magnify these fluctuations, it forced them to synchronize. Imagine a vast orchestra where each musician is playing a random note. If you suddenly stretch the entire concert hall to an enormous size in a fraction of a second, the sound waves would be pulled and smoothed, forcing all the random notes to align into a single, coherent chord that resonates across the entire space. This is what inflation did to the quantum fields. It took their random jitters and organized them into a coherent pattern of fluctuations that were consistent across vast, seemingly disconnected regions of space. When inflation ended, this coherent pattern of quantum fluctuations was imprinted onto the distribution of matter and energy. Slightly denser regions born from those coherent quantum seeds had slightly stronger gravity. These regions then attracted more matter, growing over eons into the cosmic structures we see. But the most stunning evidence is that this coherent pattern was also imprinted directly onto the cosmic microwave background. The photons released during recombination carried with them the memory of the density variations they were born into. A photon escaping a slightly denser region had to use a little more energy to climb out of that region's stronger gravitational pull, and in doing so, it lost a tiny amount of energy, making it appear slightly cooler to us. A photon from a less dense region would appear slightly warmer. Those tiny temperature differences we see in the microwave background are a direct map of the density variations in the infant universe, which are themselves a direct map of those first coherent quantum fluctuations. The patterns we see are not just any patterns. Their statistical properties match the predictions for a coherent quantum state that was stretched by inflation with stunning accuracy. The distribution of hot and cold spots, their sizes, and their correlations across the sky are exactly what physicists would expect if the universe's initial state was one of synchronized quantum harmony. It is as if we are looking at a photograph of the universe's quantum mechanical birth, a baby picture that reveals its first coordinated act. The cosmic microwave background is therefore much more than ancient light. It is the ultimate archaeological dig, revealing the deepest layer of our cosmic history and providing some of the strongest observational evidence that the universe began not in chaos, but in a state of profound, large-scale quantum coherence that set the stage for everything to come. But to venture even deeper, we must now explore a theory that rebuilds the very fabric of reality from the ground up. While string theory proposes tiny, vibrating strings, another profound approach suggests that space and time themselves are woven from a network of individual, discrete loops. This is loop quantum gravity, and it offers a breathtakingly unique perspective on that first moment of cosmic coherence. In this framework, the universe's initial synchronization wasn't about fields or particles, but about the fundamental grains of spacetime itself suddenly locking into a harmonious pattern. Let's try to visualize this. Imagine you're looking at a beautifully woven tapestry from a distance. It appears as a single, smooth, continuous image. But if you bring your eye right up to the fabric, you see that the image is actually composed of thousands of individual, interwoven threads. Loop quantum gravity suggests that the smooth, continuous spacetime described by Einstein is that tapestry. And the individual threads are tiny, one-dimensional loops of gravitational field woven into a complex network. These are the quanta of space, the absolute smallest possible units of volume. Before the universe's first coherence, this network was a chaotic, tangled mess. The connections between these loops were fluctuating wildly. There was no consistent geometry, no clear definition of distance or direction. It was a foamy, probabilistic sea of potential spaces. The pivotal moment of coherence, according to this theory, was when this frenetic network of spacetime loops suddenly organized. Through a process governed by the mathematics of spin networks, these individual loops began to connect in a stable, consistent way. Their interactions became coordinated, and a single, unified geometry emerged from the chaos. It's like watching a million tangled necklaces suddenly untangle themselves and snap into place, forming a single, glittering, interconnected web. This was the moment the quantum foam of spacetime crystallized. The wildly fluctuating connections between loops stabilized, and for the first time, a continuous fabric was born. The individual pixels of reality synchronized their behavior, creating the seamless stage upon which particles could later perform. This initial coherence of the spacetime network is what established the fundamental rules of our reality as we know it. The speed of light, the strength of gravity, the very fact that we experience 3 dimensions of space and 1 of time, these are not arbitrary numbers. They are the emergent properties of how this underlying spin network is wired. The specific way in which the loops achieved coherence determined the large-scale geometry of our universe. In this view, the famous conflict between Einstein's smooth spacetime and the granular, probabilistic nature of quantum mechanics simply vanishes. They are both correct, but they are describing different levels of reality. Quantum mechanics describes the behavior of the individual loops, the threads. General relativity describes the behavior of the coherent network, the smooth tapestry that emerges from those threads. The theory suggests we don't perceive the granularity because the coherence is so perfect and complete that the underlying discreteness is hidden from view. much like you don't see the individual pixels on a high-resolution screen. The universe's first act of synchronization was so effective that it perfectly masked its own quantum origins, presenting us with a continuous, predictable stage for the entire cosmic drama. But to truly grasp the elegance of this idea, we must first understand what supersymmetry actually proposes. In our current standard model of particle physics, the universe is built from two distinct families. On one side, we have the matter particles like electrons and quarks. These are known as fermions, and they are the building blocks of everything you can touch. On the other side, we have the force carriers like photons and gluons. These are called bosons, and they are the messengers that ferry the fundamental forces between the matter particles. For decades, this model has worked brilliantly, but it also feels incomplete, like a puzzle with a piece missing. The two families are treated separately with different rules and properties. Supersymmetry, often called SUSY for short, proposes a breathtakingly beautiful solution. It suggests that this fundamental divide is an illusion. For every known fermion, there should be a superpartner boson, and for every known boson, a superpartner fermion. The electron, a fermion, would be paired with a selectron, a boson. The photon, a boson, would be paired with a photino, a fermion. This symmetry would unite matter and force into a single, elegant mathematical framework. Now, project this idea back to the universe's first moments, a time of unimaginable energy where the distinction between matter and force had not yet hardened. In that seething cauldron, these proposed superpartners would not have been rare exceptions. They would have been everywhere, popping in and out of existence in a frenetic dance. The supersymmetry coherence hypothesis suggests that this entire zoo of particles was the key to the universe achieving its first stable, coherent state. In the extreme heat, the superpartners would have been in perfect balance. For every particle collision that threatened to push the system toward instability, the presence of its superpartner provided a counterbalancing interaction, a kind of cosmic damping mechanism that kept the wild quantum fluctuations in check. It was this delicate, balanced interplay between the two families that allowed the entire system to settle into a synchronized, low-energy state rather than flying apart or collapsing into chaos. This initial coherence, mediated by supersymmetry, would have been the bedrock upon which our entire physical reality was built. One of the most profound implications involves the mass of the Higgs boson, the particle that gives all other particles their mass. In the standard model alone, quantum corrections should drive the Higgs mass to an astronomically high value, making the existence of atoms, stars, and life impossible. This is the infamous hierarchy problem, but in a supersymmetric universe, the contributions from fermions and their bosonic superpartners would perfectly cancel each other out. The positive and negative corrections would be in exact balance, naturally keeping the Higgs mass, and by extension the mass of all familiar particles, at the low, stable value we observe. This precise cancellation isn't just a mathematical trick, it is a direct consequence of that primordial coherence. The universe could only achieve the delicate stability required for long-term structure because supersymmetry provided the necessary harmony between the particle families at its birth. Yet, if supersymmetry was so crucial at the beginning, where are all these superpartners today? This is the great modern mystery of particle physics. The theory suggests that as the universe expanded and cooled, this perfect symmetry was broken. The superpartners, once massless and abundant, became extremely heavy and decayed away almost instantly, fading from the observable universe. Their fleeting existence was just long enough to perform their most critical task, guiding the infant cosmos into a stable, coherent configuration. Their lasting legacy is not their continued presence, but the stable reality they made possible. The search for these particles at facilities like the Large Hadron Collider is, in a very real sense, an archaeological dig into the first moments of time, a hunt for the hidden architects of cosmic coherence, whose work was done 13.8 billion years ago, but whose fingerprints might still be faintly detectable in the precise laws of nature they left behind. This journey from the frenetic foam of spacetime to the elegant dance of particles leads us to a pivotal and deeply counterintuitive question. How could a system defined by its inherent randomness and unpredictability ever produce something as stable and orderly as our universe? This is the domain of quantum chaos theory, a field that explores the surprising boundary where the probabilistic world of quantum mechanics meets the sensitive, turbulent dynamics of classical chaos. Our 21st theory proposes that the universe's first great coherence was not a gentle awakening, but a spontaneous phase transition, a sudden, system-wide shift from chaos to order, much like a raging storm giving way to a perfectly still, crystalline calm. To understand this, we must first reframe our image of the infant cosmos. It wasn't merely empty or quiet. It was a system of unimaginable complexity, buzzing with ultra-high-energy quantum fields fluctuating with wild, unpredictable abandon. This was a state of true quantum chaos where the concept of a predictable outcome was meaningless. In this maelstrom, the behavior of the system was so exquisitely sensitive to its initial conditions, a hallmark of classical chaos, that any semblance of long-term order seemed impossible. It was a cosmic cacophony where every possible vibration, every potential particle interaction was happening at once in a dizzying superposition. The path forward wasn't just unclear, it was every path at the same time. The mechanism for escape, according to this theory, lies in a concept known as dynamical localization. In classical chaos, a system can explore its entire phase space. Think of a frenetic billiard ball ricocheting off every possible bumper on a table. But in the quantum realm, something remarkable can happen. The wave-like nature of particles can cause destructive interference, effectively trapping the system in a small subset of all its possible states. It's as if that billiard ball, instead of bouncing everywhere, suddenly finds itself confined to a specific, orderly pattern on the table. This transition from global exploration to localized order isn't gradual, it's a sudden phase change. The theory suggests that as the universe expanded and its energy density dropped, it crossed a critical threshold. The chaotic quantum fields, which had been exploring every possible configuration, suddenly underwent a process of dynamical localization. Their wave functions began to interfere with themselves in a way that suppressed the chaos and amplified a specific, stable, and coherent set of vibrations. The noise cancelled itself out and a pure, singular tone emerged. This mirrors what we see in certain complex systems today, like the phenomenon of synchronization in fireflies. Initially, thousands of fireflies in a swamp will blink at random, a chaotic light show with no pattern. But then, gradually at first and then all at once, they begin to blink in perfect unison. No central conductor tells them to do this. It is a self-organizing phenomenon emerging from their simple interactions. The quantum chaos-to-order transition theory applies this same principle to the very foundations of reality. The first particles and fields weren't waiting for an external command to synchronize. Their own intrinsic interactions, governed by the laws of quantum physics, reached a tipping point. The chaotic flickering of the primordial quantum fields hit a critical density of connections, and just like those fireflies, they spontaneously fell into a coordinated, coherent rhythm. The universe didn't need a conductor, it was its own orchestra, finding harmony through the sheer weight of its own interconnectedness. This spontaneous emergence of order from chaos provides a powerful and elegant explanation for the fine-tuning problem. We look at the constants of nature, the strength of forces, the masses of particles, and they seem perfectly calibrated for a coherent, life-bearing cosmos. The chaos-to-order transition theory suggests this isn't a miraculous coincidence. Instead, it was the only possible outcome. The specific, stable state our universe settled into wasn't chosen from an infinite number of possibilities. It was the inevitable attractor state, the single, most stable configuration that a system of quantum fields could possibly fall into as it cooled and localized. The laws of physics we observe are not arbitrary. They are the necessary, self-organized product of a system transitioning from maximum chaos to maximum stability. In this light, our coherent universe isn't a baffling exception to the rule of randomness. It is the most natural and probable consequence of it. For decades, one of the most debated ideas in all of physics has been the notion of hidden variables, the suggestion that the bizarre, probabilistic nature of quantum mechanics isn't the final word. That beneath the seeming randomness there might be unseen factors, deterministic rules we simply haven't discovered yet, that dictate exactly how particles will behave. This idea was largely set aside after John Stuart Bell's famous theorem, and the experiments that followed seemed to confirm that no local hidden variables could explain the spooky connections of quantum entanglement. The prevailing view became that the quantum world is fundamentally probabilistic, that particles truly don't have definite properties until they are measured. But what if we've been thinking about hidden variables on too small a scale? What if they aren't local to individual particles, but are instead global, cosmic properties that govern the entire universe at its birth? This 22nd theory, the hidden variables revelation, dares to propose that the universe's first and most profound quantum coherence was not random or probabilistic, but was dictated by a set of cosmic hidden variables that wired reality for synchronization from the very start. To grasp this cosmic scale twist on the idea, we need to revisit why local hidden variables were thought to be impossible. The classic example is two entangled particles shot off in opposite directions. According to quantum mechanics, measuring the spin of one instantly determines the spin of the other, no matter the distance. If hidden variables local to each particle were controlling this, information would have to travel faster than light to coordinate them, violating relativity. Bell's theorem provided a way to test this, and experiment after experiment has shown that the correlations between particles are stronger than any local hidden variable theory could possibly account for. The conclusion was that there are no secret dice rolls happening inside each particle that predetermine their state, but this only rules out local hidden variables, factors attached to the particles themselves that don't communicate. It leaves the door wide open for non-local hidden variables, factors that are part of the global environment or the fabric of reality itself, influencing everything simultaneously. This is where the theory makes its grand leap. Imagine the conditions of the very early universe. It wasn't a vast, empty space with particles flying apart. It was an incredibly small, incredibly dense, and utterly unified system. In that environment, the very concept of local breaks down. Everything was in contact with everything else. The theory proposes that the hidden variables we've been searching for aren't hidden inside particles. They were hidden in the initial conditions of the cosmos itself. These wouldn't be variables like a secret speed or direction for each electron. They would be more like fundamental, pre-geometric parameters that set the stage for how quantum fields would interact. Think of them as the cosmic equivalent of the rules of harmony in music. They don't dictate every note every instrument will play, but they create the framework, the key, the scale, the tempo that makes a symphony possible and ensures all the musicians can play in tune. These hidden variables would have been the universal rules of engagement that made large-scale quantum coherence not just possible but inevitable. What might these cosmic hidden variables look like? They could be properties we haven't yet identified, dimensions beyond the three of space and one of time we experience, or aspects of quantum gravity that only manifest at energies we can no longer access. Their effect would have been to correlate the quantum fluctuations of the infant universe on a massive scale, ensuring that when particles did emerge, they were already part of a synchronized network. This would resolve one of the biggest puzzles of the cosmic microwave background, its stunning uniformity and the specific, coherent pattern of its tiny variations. From this perspective, those patterns aren't the magnified result of random quantum jitters. They are the direct signature of those cosmic hidden variables at work, a fossilized imprint of the deterministic rules that guided the universe into its first stable state. The universe didn't randomly choose to be coherent. It was following a deeper, hidden script written into its very first moment. This idea doesn't overturn quantum mechanics. It simply suggests that its probabilistic nature is what emerged after the fact, once the universe expanded and cooled, and those initial global hidden variables became frozen in, their work mostly done. The apparent randomness we see in particle collisions today is real, but it exists within a framework that was decisively set up for order and structure at the cosmic scale. The hidden variables revelation theory offers a breathtaking synthesis. It allows for the weird, probabilistic quantum world that experiments confirm, while also providing a deterministic, causal explanation for the greatest miracle of all, the fact that a coherent, life-giving universe exists at all. It suggests that if we could ever rewind the tape of the universe back to the very beginning and run it again, those same hidden variables would ensure the same outcome, the same laws of physics, the same synchronized quantum fields, and the same potential for galaxies, stars, and conscious beings to eventually emerge and wonder how it all came to be. Yet this constant observation isn't simply a passive process. It can have a dramatic and counterintuitive effect on the quantum system itself. This brings us to one of the strangest and most fascinating phenomena in all of quantum mechanics, the quantum Zeno effect. Named after the ancient Greek philosopher Zeno of Elea and his paradoxes about motion, the effect states that a quantum system can be prevented from evolving or decaying simply by measuring it repeatedly and rapidly. It's as if you could stop a pot of water from boiling by lifting the lid to check on it every fraction of a second. The constant act of observation effectively freezes the system in its initial state. In laboratory experiments, this is precisely what happens. Unstable particles that would normally decay in nanoseconds can be kept in their original state almost indefinitely if they are observed continuously. The act of measurement resets the quantum clock over and over again, holding reality in a sort of stasis. Now, let's project this bizarre quantum quirk onto the grandest canvas imaginable. The infant universe was the ultimate unstable quantum system, teetering on the brink of collapsing from a coherent state back into a formless chaos. According to this 23rd theory, the quantum Zeno effect wasn't just a laboratory curiosity. It was the cosmic glue that held reality together in its most fragile first moments. The theory proposes that the universe's initial coherence was so fragile, so susceptible to the relentless pull of decoherence, that it required constant monitoring to maintain its existence. But in a universe with no external observer, what or who was doing the measuring? The answer is as elegant as it is profound. The universe was observing itself. In that unimaginably dense and interconnected primordial state, every quantum fluctuation was in intimate contact with trillions of others. There was no such thing as isolation. Each interaction between particles, each collision between fields, acted as a tiny, spontaneous measurement event. A particle didn't need a scientist in a lab coat to be observed. It was being continuously measured by the frenetic environment of the early cosmos itself. This created a feedback loop of staggering proportions. The universe's own incredible density provided the mechanism for constant self-observation, and this relentless internal measurement, happening at a rate far beyond our comprehension, triggered the quantum Zeno effect on a cosmic scale. It effectively froze the entire system in its initially coherent state, preventing it from decaying back into quantum noise long enough for that coherence to become stable and self-sustaining. The universe, through its own frantic activity, held its own wave function in place, giving itself the time it needed to truly be born. This perspective offers a breathtakingly elegant solution to a fundamental problem of cosmic origins, the transition from the quantum realm to the classical world. How did a universe governed by fuzzy probabilities become the definite, structured reality we see today? The cosmic Zeno effect theory suggests that the early self-observation was so intense that it forced a premature collapse of the wave function everywhere at once. The universe didn't gradually emerge from possibility. It was rapidly and repeatedly pinned down into a specific reality by its own internal interactions. This constant pinning action is what carved the first durable structures out of the quantum foam, locking in the initial density variations that would later become galaxies. The effect didn't last forever. As the universe expanded and diluted, the frequency of these self-measurements dropped below the critical threshold needed to maintain the freeze. The quantum Zeno effect released its grip, and the universe was finally allowed to evolve and cool into the complex cosmos we know. But by then, the job was done. The coherence was baked in, its patterns set, all thanks to a universe that, in its first frantic moments, watched itself so intently that it dared not change. But to truly grasp the significance of this theory, we must first understand the nature of the state it seeks to escape. Thermal equilibrium is the ultimate cosmic dead end. It's the state of maximum entropy where energy is perfectly and uniformly distributed. Imagine a cup of coffee left alone in a room. Initially, it's hot and the room is cold, a state of disequilibrium rich with potential. Heat will flow from the coffee to the room until everything settles at the same lukewarm temperature. At that point, the system has reached thermal equilibrium. Nothing else happens. The energy is still there, but it can no longer perform any work. It's lost all its organizational potential. It's a state of boring, featureless uniformity. Now cast this image across the entire cosmos. The classic Big Bang model suggests the universe began in a state of incredibly low entropy, a condition of exquisite but ultimately unstable order. The thermal equilibrium coherence breakthrough theory offers a radical alternative. It proposes that perhaps the very early universe was actually in a state of perfect or near-perfect thermal equilibrium. It wasn't a smooth soup of potential. It was a lukewarm bath of maximum randomness, a cosmos where nothing could happen because everything was already in perfect, boring balance. So how did we get from that sterile uniformity to the dazzling complexity we see today? The catalyst, according to this theory, was a spontaneous and profound break from that equilibrium, a break that was achieved through the emergence of quantum coherence. Think of it like a vast, motionless sea, so calm that not a single ripple disturbs its surface. There is no current, no flow, no way to distinguish one direction from another. Then a single, coordinated wave begins to form. That wave is coherence. In the cosmic context, this was the moment when quantum particles and fields stopped behaving as independent, random actors and began to communicate to synchronize their states. This coordinated behavior did something remarkable. It created information. In a state of perfect thermal equilibrium, there are no differences, no gradients, and therefore no information. Every point is identical to every other point, but the moment coherence emerged, it created correlations. One region of space became subtly linked to another, not through direct contact, but through a shared quantum state. These correlations are the most basic form of information, and they broke the perfect symmetry of the equilibrium, creating the first arrows of direction and purpose in a previously directionless cosmos. This initial coherence-driven break from equilibrium is what allowed the universe to become a processor of its own information. With information now present in the form of quantum correlations, the cosmos could begin to do work. It could use those tiny differences, those information gradients, to build structures. This is directly analogous to a steam engine, which uses a difference in temperature between a hot boiler and a cold condenser to perform mechanical work. The early universe, by breaking from its thermal equilibrium through coherence, created its own primordial engine. The coherent quantum fluctuations became the pistons, and the gravitational field became the fuel, converting that initial information into the gravitational clumping that would seed the first galaxies. The universe didn't just cool down, it woke up, transforming from a passive, featureless state into an active, information processing system whose first and most important calculation was its own complex future. And now we arrive at a perspective that reframes the entire cosmic story, not in terms of energy or matter, but in the most fundamental currency of all, information. This is the quantum information theory viewpoint, and it proposes that the universe's first great coherence was the moment it booted up as the ultimate quantum computer. In this framework, the primordial cosmos wasn't a place of particles and forces, but a vast, unorganized sea of quantum bits or qubits. These weren't physical things in the way we normally think. They were the fundamental units of potential, each one a superposition of both 1 and 0, a perfect representation of possibility. The universe was a blank hard drive, buzzing with random noise, containing every possible program that could ever be run, but running none of them. It was all potential and no actuality. The pivotal shift, according to this theory, was the transition from this chaotic information soup to an organized, coherent information processing system. This wasn't merely particles starting to communicate, it was the universe executing its first line of code. Think of a modern quantum computer in its supercooled chamber. To perform a calculation, its qubits must be initialized into a coherent state. They must be synchronized, their wave functions aligned, so they can work together to explore multiple solutions simultaneously. The theory suggests that the entire cosmos underwent a similar initialization process. As it cooled through a critical threshold, a universal protocol kicked in, forcing the countless random qubits of the quantum vacuum to align their phases. The chaotic buzzing didn't just quiet down, it became a coordinated hum, a single, system-wide quantum state capable of performing a computation. The first coherence was the universe entering its boot-up sequence. This initial act of cosmic information processing would have had a very specific output, the laws of physics themselves. The theory posits that the fundamental constants, the strength of gravity, the mass of an electron, are not arbitrary numbers but the hard-coded result of that first universal computation. They are the answer the universe got when it processed its own initial conditions. The stunning fine-tuning that allows for a complex cosmos could simply be the logical, and perhaps even inevitable, solution to a specific informational input. In this light, the universe isn't a machine governed by laws. It is a computation that generates its own laws as an output. The coherent patterns we see in the cosmic microwave background are not random fluctuations. They are the readout from that first and most important calculation, the data that would later be used to structure galaxies. This perspective offers a breathtakingly elegant solution to the question of why our universe is comprehensible at all. If reality is the result of a coherent computation, then it is inherently logical and structured. Mathematics isn't just a tool we use to describe the universe, it is the native language in which the cosmic program is written. Our ability to unravel the laws of physics through logic and equations isn't a miraculous coincidence. It is a direct consequence of the fact that we are patterns within that same computation, emerging from its output and naturally speaking its language. The universe's first coherence was the moment it became intelligible, setting the stage for conscious observers to eventually arise and, in a beautiful loop of self-reference, begin to decode the very program that gave them life. Yet for all their ghostly nature, neutrinos are far from insignificant. In fact, they are the most abundant massive particles in the entire universe, outnumbering atoms by over 1 billion to 1. And this incredible abundance is the key to our next theory. The cosmic neutrino background coherence proposal suggests that these countless, silent particles didn't just witness the dawn of time, they actively shaped it, acting as the universe's first and most effective network for establishing large-scale quantum synchronization. To understand how, we need to journey back to a specific moment just 1 second after the Big Bang. At this point, the universe had cooled enough for neutrinos to finally decouple from the hot, dense plasma of electrons and protons. This event, known as neutrino decoupling, was a cosmic exodus of staggering proportions. Suddenly, these particles were set free, streaming unimpeded in every direction at nearly the speed of light. They filled the cosmos, creating a pervasive background sea known as the cosmic neutrino background, a relic even older than the cosmic microwave background. And it is within this sea that our story finds its focus. These neutrinos, with their unparalleled ability to travel vast distances without interacting, could have served as the ultimate messengers, carrying quantum information from one region of the universe to another and weaving a web of coherence across the entire observable cosmos. Imagine two regions of the early universe separated by a distance too great for light to have connected them yet. According to classical physics, they should be completely independent, unable to influence each other. But the quantum world operates by different rules. If a neutrino born in one region were to travel to the other, it could carry with it subtle quantum information, a phase, a spin orientation, a specific vibrational state. Because neutrinos barely interact with anything, this information wouldn't get scrambled or lost along the journey. It would be delivered pristine to its destination. Now multiply that single neutrino by the countless trillions that were streaming everywhere. This creates a dizzying network of quantum communication, a constant exchange of information that could have forced wildly distant and seemingly separate quantum fields to fall into sync. It's as if the entire universe was wired together with invisible quantum threads, each one a neutrino, ensuring that every part of the cosmic orchestra was reading from the same sheet of music. This neutrino-mediated coherence would have been the subtle architect of the large-scale structure we see today. The theory posits that the synchronized quantum fluctuations that were imprinted on the cosmos, the seeds for all future galaxies, weren't just smoothed by inflation. Their specific, correlated patterns might have been finalized and reinforced by this constant neutrino background. These ghostly particles, by providing a mechanism for long-range quantum correlation, could have ensured that the tiny density variations were not random, but were part of a coherent, universe-wide pattern. The great cosmic web of galaxies and voids we observe in the night sky might not just be a fossil of quantum fluctuations, but also a fossil of the neutrino network that helped to lock those fluctuations into place, stitching together the fabric of reality with its silent quantum threads. But to truly grasp how something as ephemeral as quantum information could fuel the cosmos, we must turn to a field that merges the two most powerful theories of change, thermodynamics and quantum mechanics. This emerging discipline, quantum thermodynamics, reframes the birth of the universe not as an explosion, but as the startup of the ultimate energy conversion device. Our next theory proposes that the universe's first quantum coherence was the moment this cosmic engine achieved peak performance, transforming the raw, chaotic heat of creation into the structured, usable work of a new reality. Classical thermodynamics gave us the laws that govern steam engines and refrigerators, centered on the relentless rise of entropy, the universal slide from order to disorder. It tells us that no engine can be 100% efficient. Some energy is always lost as waste heat, but at the quantum scale, these rules get a fascinating rewrite. Quantum thermodynamics explores how tiny systems can defy classical limits, using coherence to achieve near-perfect efficiency. Imagine an engine so small it's made of just a few atoms. At this scale, the weird rules of quantum mechanics take over. Particles can tunnel through barriers, exist in superposition, and become entangled. An engine leveraging these effects isn't limited by friction or heat loss in the same way. It can, in theory, approach 100% efficiency by harnessing coherence to direct every bit of energy toward useful work. Now apply this concept to the universe in its first moments. It wasn't a vast, empty space. It was an unimaginably dense, hot, and tiny system, the ultimate quantum-scale environment. This theory suggests it was also the ultimate quantum heat engine. The hot reservoir was the incredible energy density of the initial singularity or inflattened field. The cold reservoir was the rapidly expanding space itself, cooling as it grew, and the working fluid was the quantum vacuum and its fields buzzing with potential. For this engine to run, it needed a piston, a mechanism to convert that heat into work. The theory posits that the piston was the achievement of quantum coherence itself. As the universe expanded and cooled, it crossed a threshold where the frenetic quantum fluctuations could no longer remain random. They were forced to synchronize to become coherent. This shift wasn't just a change of state. It was the moment the engine engaged, transforming the disordered thermal energy into the organized work of creating the first particles and sculpting the first density variations in spacetime. This initial coherence didn't just make the engine run, it made it run with staggering efficiency. The synchronized quantum state allowed the system to avoid the classical thermodynamic waste. There was no random scattering of energy. Instead, the coordinated behavior of the quantum fields directed the energy precisely where it needed to go, like a perfectly choreographed dance where not a single step is misplaced. This maximum efficiency could explain one of the great mysteries of our universe, its astonishing longevity and stability. If the cosmic engine had been even slightly less efficient at that first moment, if more energy had been lost to quantum friction or decoherence, the initial density fluctuations might have been too weak to ever collapse into galaxies, or the universe might have rapidly collapsed back on itself or flown apart into a useless haze. The fact that we are here in a complex, structured cosmos 13.8 billion years later is a testament to the flawless first cycle of the universe's quantum heat engine, a cycle that set in motion everything that was to follow. Imagine a stone dropped into a still pond. The initial splash sends ripples spreading outward, but when the water finally settles again, the pond isn't exactly the same. The water level at the center is permanently, if infinitesimally, lower. The passing wave leaves a lasting change in the very geometry of the pond itself, a permanent displacement known as memory. Now take this concept and scale it up to the most violent event imaginable, the birth of the universe. According to this theory, the universe's first great act of quantum coherence wasn't a silent event. It was a cataclysm that sent literal shockwaves through the fabric of spacetime, ripples so powerful they left an eternal scar, a permanent deformation woven into the cosmos that might still be detectable today. These are not the fleeting gravitational waves we detect from black hole mergers. These are gravitational waves with memory, and they could be the ultimate cosmic archive. To understand how this memory is imprinted, we need to consider what gravitational waves actually are. In Einstein's theory of general relativity, gravity isn't a force pulling through space, it's the curvature of spacetime itself. Massive objects like stars and planets warp this four-dimensional fabric. When such objects accelerate violently, like two black holes spiraling into each other, they create ripples in spacetime that propagate outward at the speed of light. These ripples are gravitational waves. They literally stretch and squeeze the space between objects as they pass by, an effect so tiny it requires instruments like LIGO to detect. But a gravitational wave with memory is different. It doesn't just stretch and then contract space back to its original shape. It stretches it and leaves it that way. The passing wave delivers a permanent DC shift, a lasting change in the separation between two test masses, long after the wave itself has gone. The gravitational wave memory theory proposes that the most dramatic event to ever cause such a permanent shift was the universe's transition into its first coherent state. Think of that moment not as a gentle awakening, but as a profound phase transition of reality itself, the entire cosmos shifting from a chaotic quantum foam into a synchronized, ordered system. This wasn't a local event, it was a system-wide change in the energy and stress distribution of the entire universe. In the language of general relativity, such a massive, sudden redistribution of energy momentum is the most powerful source of gravitational waves imaginable. The theory suggests this coherence event generated a deafening burst of gravitational radiation, a primeval thunderclap echoing through the newborn spacetime. And because the change was permanent, the universe didn't snap back to its incoherent state. The gravitational waves generated carried that permanence with them. They were born with memory. The incredible promise of this theory is that these memory-carrying waves might still be washing over us. Unlike the high-frequency chirp from a black hole merger that lasts less than a second, these primordial waves would have been stretched by the universe's expansion into a low, constant hum, a background sea of gravitational radiation permeating all of reality. This is the gravitational wave equivalent of the cosmic microwave background, but it comes from a much, much earlier time. Detecting this background would be like finding a recording of the universe's first cry. But the real treasure within this signal would be the specific, permanent deformation encoded within it, the memory. That eternal scar wouldn't just tell us that a big event happened. Its specific pattern could reveal the precise nature of the coherence that caused it. Did the field synchronize in a smooth, uniform wave, or was it a more turbulent, patchy process? The memory imprint would hold the answer, acting as a direct fingerprint of the universe's first organized state. The hunt for this signal is already driving the design of the next generation of observatories. While current detectors like LIGO are exquisitely tuned to the high-frequency waves from stellar catastrophes, they are blind to the ultra-low frequency hum of the primordial background. To listen for that, we need a much bigger instrument. Projects like the Laser Interferometer Space Antenna, or LISA, propose placing 3 spacecraft millions of miles apart in orbit around the Sun, creating a gravitational wave observatory with an arm length equal to the distance between the Earth and the Sun. Even more ambitious concepts involve using the precise timing of pulsars highly magnetized, rotating neutron stars that act as cosmic lighthouses with unbelievable regularity. By monitoring a network of these pulsars across our galaxy, scientists could detect the faint nanohertz gravitational waves that would ever so slightly alter the arrival time of their pulses, a project known as a pulsar timing array. These are the tools that could one day tune into the universe's deepest memory, listening for the faint but eternal echo of its first moment of harmony. What if the same strange quantum effects that allow a robin to navigate across continents using Earth's faint magnetic field, or that enable photosynthesis in plants to be almost 100% efficient, were also the very same forces that orchestrated the birth of the cosmos itself? This is the radical proposition of the quantum biology cosmic extension theory, an idea that bridges the gap between the very small and the very large, suggesting that the principles we see governing life today are actually a faint echo of the universe's first and most fundamental behavior. To understand this, we first have to venture into the surprising world of quantum biology. For a long time, we thought the quantum world, with its superposition, entanglement, and tunneling, was confined to the realm of isolated atoms and ultra-cold laboratories. The warm, wet, and messy environment of a living cell seemed like the last place delicate quantum coherence could survive. Random collisions with water molecules and thermal noise should instantly shatter any fragile quantum state. But groundbreaking research has revealed that nature has indeed mastered the quantum realm. We now see evidence that migratory birds have a compass in their eyes relying on entangled electron pairs sensitive to the planet's magnetic field. In photosynthesis, plants use quantum coherence to guide energy from sunlight to the reaction center with near-perfect efficiency, essentially shopping for the shortest path among all possible routes simultaneously. Life doesn't just exist in a classical world, it actively harnesses the spooky laws of quantum physics to thrive. The quantum biology cosmic extension theory asks a breathtaking question. What if this isn't a clever trick that life invented much later? What if it's a remnant, a cosmic habit left over from the very beginning? This theory posits that the ability to maintain quantum coherence in complex, dynamic environments isn't an evolutionary innovation, but a primal feature of the universe that was present at its inception. In this view, the first biological organisms that learned to exploit quantum effects weren't discovering something new. They were simply tapping into the oldest rhythm of all, the same synchronized beat that brought the cosmos into being. Life isn't fighting against the classical world to use quantum mechanics. It's simply remembering how the universe originally worked and putting those ancient tools to new use. This shifts our entire perspective on that first moment of coherence. Rather than imagining a stark, sterile vacuum where quantum fields synchronized in perfect isolation, this theory suggests the early universe might have shared more in common with a living cell than with a particle accelerator. It was a dense, interactive, and dynamic system, a kind of cosmic protoplasm buzzing with potential. Within this system, the same principles that now allow quantum effects to persist in biology, principles like environmental screening and self-organization, could have protected and enhanced the first cosmic coherence. The incredible density of the infant universe wouldn't have necessarily destroyed quantum effects. It might have provided a structured environment that actively nurtured them, much like the complex molecular structures in a plant cell protect energy from decoherence as it travels. The universe didn't achieve coherence in spite of its complexity. It achieved coherence because of it, using its own innate, biological-like organizational principles to synchronize itself into existence. This leads to a truly profound implication. The universe may not be a cold, mechanical clockwork, but something far more organic and alive in its fundamental nature. The fact that quantum coherence is now integral to life might not be a coincidence at all. It could be a sign that the universe has always had a predisposition for life, not in a mystical sense, but in a deeply physical one. The same properties that allowed for coherent quantum fields to form the first galaxies are the very same properties that, billions of years later, would allow a plant to turn sunlight into food and a bird to find its way home. We are not separate from the universe's quantum origins. We are a continuing expression of them. Our biology is a living testament to the universe's first and most important habit, the habit of acting in synchrony, of connecting across distances, and of turning chaos into coordinated, breathtaking complexity. This brings us to our final and perhaps most mind-expanding theory, one that asks us to consider the very nature of existence not as a physical event, but as a mathematical necessity. What if the universe's first quantum coherence wasn't caused by a particle, a field, or a force, but by a concept? What if mathematics itself is not merely the language we use to describe reality, but is in fact the fundamental substance from which reality is made? This is the core of the mathematical universe coherence hypothesis, a proposal so profound it suggests that the cosmos we inhabit is, at its heart, a complex mathematical structure that achieved coherence simply because it could. To truly wrap our minds around this, we need to step back from our everyday intuition that the universe is made of physical stuff, atoms, energy, space-time. Instead, consider the possibility that these are all secondary phenomena, merely the shadows cast by a deeper, abstract reality. In this view, mathematics isn't invented by humans, it's discovered. The relationships and structures we find in algebra, geometry, and logic exist independently of us in a vast, timeless Platonic realm of perfect forms. A circle is perfectly round, and 2 plus 2 always equals 4, regardless of whether any human or any universe is around to acknowledge it. The mathematical universe hypothesis, championed by thinkers like Max Tegmark, takes this idea to its ultimate conclusion. It proposes that our physical reality is one of these mathematical structures. Specifically, it is a mathematical structure that has the property of containing self-aware substructures, like us, who can observe and describe it. But how does a static, abstract mathematical structure become the dynamic, evolving universe we experience? This is where the concept of quantum coherence makes its grand entrance. The hypothesis suggests that the transition from a mere abstract possibility to a concrete physical reality was mediated by the universe's first great act of quantum synchronization. Think of it like a beautiful piece of sheet music sitting on a stand. The notes and the structure are all there, but it remains silent, a world of pure potential. Then an orchestra begins to play. Each musician reads the same score, and through an act of collective coherence, they bring that mathematical structure to life as sound. In the same way, the mathematical universe coherence hypothesis posits that the mathematical structure of our universe sounded itself into existence through quantum coherence. Countless potential mathematical states existed, but only those capable of achieving a stable, self-consistent coherence, a kind of mathematical harmony, could actually manifest as a physical reality. This initial coherence would have been the process that selected our particular universe from the endless landscape of mathematical possibilities. Why do we have 3 dimensions of space and 1 of time? Why do the fundamental constants have the precise values they do? In this view, these aren't arbitrary choices or the result of random chance. They are the necessary, logical consequences of a specific mathematical structure that was stable enough to achieve coherence. Other mathematical structures might exist in the abstract, but they could be inherently unstable, incapable of sustaining the synchronized quantum states needed to boot up into a physical reality. They would remain silent, unplayed symphonies. Our universe is the one that worked. Its first quantum coherence was the moment its mathematical blueprint became audibly real, its equations ringing true across the void and setting in motion the magnificent chain of events that led to us. We are not just living in a universe described by math. We are living inside the math itself, and our conscious observation of it is the universe becoming increasingly aware of its own beautiful and ultimately mathematical nature. From the cosmic symphony of synchronized strings to the silent networking of ancient neutrinos, from a universe booting up as a quantum computer to the profound possibility that mathematics itself is the fundamental substance of reality, our journey through these 30 theories reveals a cosmos far stranger and more magnificent than we could have ever imagined. We've explored how the shattering of perfect symmetry might have given birth to the first rhythm of matter, how a period of violent inflation could have smoothed quantum jitters into a cosmic blueprint, and how the entire observable universe might be a holographic projection from a 2-dimensional boundary. We've considered the radical idea that spacetime itself crystallized from a quantum foam, and the even more astonishing proposal that consciousness may not be a product of the universe, but a participant in its very creation. Each theory, in its own unique way, attempts to answer the most profound questions we can ask. Why is there something rather than nothing? How did order emerge from chaos? And what is our place in this grand cosmic story? Whether through the lens of quantum Darwinism, where stable states were selected for survival, or through the cosmic Zeno effect, where the universe held itself in existence through constant self-observation, these ideas all point toward a beginning that was not a mere explosion, but a transition. A moment of profound connection and synchronization that set the stage for everything that followed. They suggest that the laws of physics, the forces that bind atoms, and the very fabric of space and time are not arbitrary rules. but may be the inevitable outcome of a universe that found a way to be coherent, to be stable, and to be knowable. This exploration is more than just a collection of fascinating ideas. It is a testament to the human spirit's unending curiosity. It shows us that our drive to understand our origins pushes the boundaries of physics, philosophy, and metaphysics, blurring the lines between them in the most thrilling ways. These theories are not final answers, but stepping stones, each one offering a different perspective on the greatest mystery of all. They invite us to keep questioning, to keep wondering, and to look at the night sky not just as a collection of distant points of light, but as the living, breathing result of a coherence that began at the very dawn of time. Now, we want to hear from you. Which of these 30 theories resonates most deeply with your own sense of wonder? Does the holographic principle captivate your imagination, or are you drawn to the elegant balance proposed by supersymmetry? Perhaps the idea of the universe as a quantum computer or the role of consciousness in collapse speaks to you. Share your thoughts and favorite theory in the comments below. We read every single one and love continuing this conversation with you. If you've enjoyed this journey to the edge of understanding, make sure to subscribe and hit the bell so you don't miss our next exploration into life's biggest mysteries. Until then, keep looking up and wondering why.